Welcome to my YouTube channel. In this video we are going to be solving some problems under projectile motion. So the first problem is this. So during a football match, the ball kicked at 45 degrees just went over the goal post, height 2.5 meters. Assuming the goal post height is the greatest, calculate A, the speed at which the ball was projected. That means the initial speed u, and B, the time taken to reach the greatest height. Then C, the horizontal distance between the point of kick and the foot, which is more or less like the range. Okay, so let's see a diagram that depicts such scenario. So once the ball is launched from this point, goes over, the goal post is assumed to be this height, and it is the greatest height. So we are asked to find this u needed to launch this ball so that it will just go past this goal post. That's one. Then B, the time taken to reach this greatest height, the time it will take for you to move from this point to this one. Then C, the horizontal distance between the point of kick, which is this, and this. So we have to look for this one, which is the C. Now to find the speed, there are several formulas that we can use. So let's consider the formulas that are available. We can use this formula. Now for us to use this formula, we must know the height y, which is this. We must know our initial we must know our time. We are asked to look for this. We must know our time. We already know our theta, which is 45. We know g. Since we don't know our time and we are asked to look for u, that means we cannot use this formula. Another formula we can use is this. We have our y, which is the height of the goal post. We are asked to look for u. Our x is not known because we are asked to look for it. So for the fact that the x is not known, we cannot use this formula. Then another formula we can use again is this. Remember, this formula was derived in the previous video under projectile motion. So if you look at this, we are asked to look for this. Theta is given, y is known, g is a constant, but this vy squared, it's the velocity at this point. We can see that it is 0. When it gets to the maximum, it is 0, so we can use this formula. So vy squared will be set to 0 because when it gets to the greatest, the vertical height is what? The velocity in that y component is 0. So we stick with this formula. So that gives us 0 equal to u squared sine squared theta minus 2g. Then we have this one coming to the other side. Then we have this expression. So in this place now, we are going to make u squared, or u the Soviet formula, and this one comes down. We have this. Then take the square root of both sides. You have this. And if you notice, this formula can be used to solve the can be derived from the maximum heights for a particular projectile motion. The maximum height reached, the formula for maximum height it looks like it. So once we plug in our values, then u comes out. So 2 times 9.8 times 2.4, which is the height, divided by sine 45 all squared. Then finally our u is equal to 9.699 meter per second. So we'll go to the next problem, which is the time taken to get to the maximum height, and the formula to use is t equal to u sine theta all over g. We now know our u, we know sine theta, and we know our g. We plug them in and we get our answer. T equal to the initial velocity, the launch velocity, sine 45 all over this, and we get our time to be 0.699 seconds. And if you want to know the total time taken to get to the floor from point of launch to the ground to the other side, just multiply this one by 2. Okay, so the next problem is the horizontal distance, which we showed in that diagram. So we can use this formula. So but let's see what and what are known and what are not known. Our y is known, which is 2.4. Our x is what we are asked to look for. We know our theta, which is 45. We know our u, we know our theta, so we can use this formula to get the value of x, and that will lead to a quadratic equation. We can also use this formula, x equal to ut cos theta. We are asked to look for this x. We know our u, we know our t, we know this. If you look at both sides, it is easier to use this one. So let's stick with this. So x equal to the velocity times the time times cos 45, and that gives us x equal to 4.79 meters, which is the horizontal range from the foot of the goalpost to the point where the ball was kicked. So let's look at another problem again and see how we can apply some of this formula. Problem 2. A coin is thrown from the top of a building upward at an angle of 30 degrees to the horizontal with an initial speed of 20 meters per second. If the height of the building is 45, how long does it take the coin to reach the ground? What is the speed of the coin just before it strikes the ground? What is the horizontal distance from the foot of the building to the point where the coin hits the ground? Right, so let's look at the diagram that depicts something of this form. So this is a diagram. The height of the building is 45. The horizontal range from the foot of the building to where it will land is not known, which is x. The launch velocity is 20. The angle there is 30 degrees. So we are asked, how long does it take the coin to reach the ground? So we want to find the time it takes from the launch to the ground. So there are several formulas that can be used to solve for the time. Let's look at one of them. X equal to ut cos theta. So we need our t, we know our u, we know our theta, but we don't know x, so we'll drop this formula. So if we look at this one, we know our y, we know our u, we know our theta, g is a constant, then we can use this particular formula, which will lead to a quadratic equation. But to use this formula, take note, we know what our u is, 20 meters per second. Our t is what we are going to find. Theta is 30. All these other ones are okay. But for the y, the value it will take, we're giving 45. Take note, when you launch from the start and it goes and gets to this point and goes beyond below the starting point, then y will take negative value. But if you launch and it doesn't go below this starting point, this level, then it takes negative value. But as long as the point goes below, then it takes negative value. So with this case, our y will now be minus 45. We fix in our ut, our theta, then this, and that gives us minus 45 equal to 20 times this minus all this. If we rearrange, it gives us minus 45. This times sin 30 will give us 10t minus 49. So if we multiply everything by minus and send this one back, we'll have something of this form. And this can be solved using the quadratic equation. And we'll be expected to get 2 times. So let's see the 2 times. So t equal to 4.218 seconds and t equal to minus 217 seconds. Because of this negative time, this one is unrealistic. So this will be our final answer for the time taken. So let's see the next problem. What is the speed of the coin just before it strikes the ground? There are several formulas we can use to calculate the speed. Now the first thing is that the speed just before it strikes the ground will be the combination of the vertical component and the horizontal component. So the vertical component is a y and the horizontal component is a x. So let's see that of x. Vx equal to u cos theta. We need to square this one because we'll need it later. So we'll square it and this is what we have. Then for the vertical component, we have this Vy u sine theta minus gt. We already know the time, so that's why we are going to use this one. We know a u, we know the theta. So if we square it, we get this one. Then finally, the u just before it strikes the ground, the velocity is going to be the square root of the addition of this and this. So that's what we have here. V equal to Vx squared plus Vy squared. So by the time we plug in the values here and this, we can find this value. Okay, so our ux squared is equal to 20, which is the initial velocity, squared cos quantity, and ux squared is 300. Let's go for our ui squared. We'll fix in the values and we'll get this expression. So at the end of the day, we'll take the square addition of these two and take square root of everything. So v equal to 300 plus this, and that gives us this. So if we take the square root of this, we'll get this as our velocity, right? So this is velocity just before it strikes the ground. So let's see the next problem. So what is the horizontal distance from the foot of the building to the point where the coin hits the ground? So to solve this problem, we are asked to find the x. So there are several formulas that can be used to find x. So we can use this formula, right? All we just need to do is fixing the value of u, which we already know, the time, which we already know, and the theta. So let's see. We know this 20, the time here, and 30. So that gives us x equal to 73.06 meters. So instead of using this one, you can also use the other one, which is this formula. Although this formula is a little bit lengthy, but we can still use it. Our y this time around will still be negative because it goes below the point of origin. So our x is what we are looking for. G is known, u is known, and theta is known. So we fix in the values. Minus 45 equal to our x is not known, which is this, tan 30 is what we have here. Then g 9.8 divided by 2 divided by our u squared gives us this, and cos squared theta gives us this. You can try it, and if you rearrange, we have this x squared minus this x minus 45 equal to 0. So if you solve this simultaneously, this is what you have. x1 equal to 73.05 meters, x2 is minus 37.711 meter. But you know this cannot be the realistic answer, so this will be the realistic answer. So if you compare this with this, you can see they are exactly the same, and that's it. So thanks for watching. I hope you enjoyed this. Please like, share and subscribe to this channel.